Dear students, we are starting a new topic today, and this topic is electric fields. Part of this topic was done in the AS, and part will finish here. This part that we are going to discuss in A2 starts with the formula that helps us calculate what force one charge exerts on the other when it is brought near another charge. It simply means when two or more charges are in the proximity of each other, they are close enough, they are in the fields of each other, how do they interact? What is exactly the force of repulsion between them or the force of attraction between them? This is basically the starting point of this chapter. And of course, there are many useful concepts related to the charges, the fields, and the interaction between them that will follow. So the first thing that we are going to discuss today is Coulombs law of electrostatics. Electrostatics is simply the study of charges when they are not moving. That means Coulombs law will be applicable on all situations in which charges are at rest, or at least they are moving at very, very slow speeds. They may be changing their positions from this to this position, but they are not rushing basically. So all those situations where charges are or may be taken at rest, we can apply this charge, which helps us calculate the force that one charge exerts on the other. This law states that force of attraction, or let me put it slightly differently, any two charges will attract or repel with a force which is directly proportional to the product of the magnitude of their charges, and is inversely proportional to the square of the separation between them, square of the separation or distance between them. So this is the statement. Any two charges, that means even if there are many charges present, we can individually consider any two. So the force that one charge exerts on the other is independent of any number of charges present around. So this is an important thing to remember. So this is between any two charges, they will attract or repel. This we know because this is the property of charges. It is not always attractive force. As we learned in the gravitational, in the case of gravity, that was always an attractive force. But now that we are going to deal with charges, it may be attractive force or repulsive force. So this force is directly proportional to the product of the magnitude of the charges. So one thing is product of the charges. Suppose this is charge Q1 and this is charge Q2. Usually Q is the letter that we use to use as a symbol for charges. So let's assume this is charge 1, this is charge 2. If they are similar charges, let's say both are positive, they will repel each other. And the magnitude of this force, or simply the force with which they are repelling each other, one thing on which that force depends is the product of the magnitude of these two charges. That means Q1 and Q2. So that force which is being felt by these two, this is directly proportional to the product. The second thing on which this force depends is the square of the separation between the charges. And it is inversely proportional to it. It is directly proportional to the product, but is inversely proportional to the square of the distance between them. That means this force is inversely proportional to the square of the distance between two charges. Suppose this is the separation between the two charges, usually denoted by R. If I combine these two, I can write them together in one relation in this manner: Q1, Q2 over R square. And if I change this into an equation, this should be some constant K, Q1, Q2 over R square. So this is the formula which is the mathematical form of the Coulombs law of electrostatics. If you look closely, you can find a few similarities with the formula that you learn in Newton's law of gravitation. In Newton's law of gravitation, the force of attraction was directly proportional to the product of the masses, and there we wrote M1, M2 if you remember. And similarly, that force was inversely proportional to the square of the distance between the centers of those masses. Here we have not written the word center because charges are already very small. They can be treated as points, and that is why we treat them as point charges. And later on, we also elaborate on few other charges which have extended dimensions, but why we continue treating them as point charges, I'll come to that again to this idea. So force which one charge is exerting on the other is now this force and this force. If this is the force that this charge is exerting on it, and this force is the one exerted by this charge on this, they are equal and opposite forces. Irrespective of the magnitudes of the two, this means Newton's third law is also is at work. Newton's third law. This law is applicable because clearly there are two objects, there are two forces, and they are equal and opposite. So if they ask you why Newton's third law is relevant here, you can refer to the forces being equal and the force that one charge exerts on the other is equal in magnitude but opposite in direction, and there are two charges involved. So third law is applicable here. Now, come to this formula, how we use this formula to calculate various forces when we know charges, when we know their separation, and what is this K basically. Let's elaborate on these few points. This constant K is actually 1 over 4 pi epsilon naught. This epsilon is a Greek letter, and this small index 0, we read it as epsilon naught. This is the permittivity of free space. Permittivity of free space. Its value is given in the data booklet, and it is 8.85 into 10 raised to power minus 12 farad per meter. No need to memorize this, and no need to learn the definition of what permittivity is, but let me give you some idea for your understanding. Permittivity has something to do with the medium in which the charges are placed. If you place the same two charges in a liquid, the force is different. If you place these two charges by drilling two holes in a solid, the force that one charge exerts on the other undergoes a change. So that means the medium in which these two charges are placed is important, and we always assume that the charges are placed in free space, vacuum, or air, because the value of permittivity is almost same for free space and air. So we continue using the same value of permittivity in this formula for all the situations, because in no situation are they going to put these charges in any different medium. So permittivity means what is the property of that medium, how easy or difficult it is for the two charges to interact from that given distance at which they are placed. So K is 1 over 4 pi epsilon naught. That means if you use this value here, 1 over 4 pi multiplied by this number, 8.85 into 10 raised to power minus 12, this gives you a number which is easy to remember, 9 into 10 raised to power 9. In SI units, which is Newton meter square per Coulomb square, if you work out the units from this formula, it is easy to see that K has this units in SI, and this is a combination of derived and base units basically, but this is how it can be expressed in a convenient way. 9 into 10 raised to power 9. That means instead of going to the formula sheet and see the value of permittivity of free space, then put in this formula 4 pi epsilon naught, then calculate it, and spending a few precious minutes in the exam to calculate that this is the value, you should memorize that K is always 9 into 10 raised to power 9 Newton meter square per Coulomb square. So this is the figure that you will learn. Of course, you will repeat this several times when you use this formula for several situations, calculating force between one charge and another. This will automatically be learned by heart. So 9 into 10 raised to power 9. That means it's a large number. Some students confuse and write -9 here, assuming that we cannot have large values for such small charges involved. So remember it for once and all, that there is a positive number, and this is obviously going to be a very large quantity, K. Of course, permittivity is very small. If you see 10 is for minus 12 there, but this is in the denominator. So when I calculate this all, this is going to be the K, I mean, it's going to be a big number. Let's see how we use this formula to calculate the force that a proton exerts on an electron when they are very, very close to each other in a hydrogen atom, for example. In a hydrogen atom, in which we have one proton surrounded by an electron, if we take the approximate distance between them, let's say 2 picometer, and we know the magnitude of the charges, proton and electron have same charges on each other. It is just opposite in sign, but the magnitude of these two charges is same. So let's apply this formula on that situation. This is a proton, and an electron is circling it, and let's assume the distance between these two is 2 picometer. They are 2 picometer apart. This is a proton, and this is an electron circling it. In a simple picture of hydrogen atom, we have a proton in the form of a nucleus at the center of it, an electron surrounding it, assuming that they are at rest. Of course, electron is moving, but this motion does not cause any change in its energy. It is constant, and the distance is assumed to be constant. So we apply this formula on it. F is equal to K Q1 Q2 over R square. Now K is 9 into 10 raised to power 9. This Q1 is charge on proton. This is E. If you go to the data booklet, the charge on proton is written as elementary charge. Charge on electron is written as elementary charge. They both are 1.66 into 10 raised to power minus 19 coulomb. So if both are identical charges, we square Q1 into Q2 becomes the same charge, I mean Q squared, divided by R square, which means 2 into 10 raised to power minus 12 whole squared. Now this is something you can give to your calculator, simplify it, and you will see that this comes out to be, as I did, 6.2 into 10 raised to power minus 5 Newton. This is the kind of force that we have between a proton and an electron when they are at this distance from each other, which is 62 micronewton. So this is the typical value of the force that one charge exerts on the other, because the magnitude of the charges are very, very small here. The distance between them are of course very small, but this is exactly due to the smallness of this distance that this force exerts. If you go on increasing the separation between them, this force continues to decrease, and this is known as inverse square rule. Inverse square rule tells us what will happen to the force if you increase or decrease the separation between the same two charges. And this is easy to understand now. If instead of 2 picometer, I make it 4 picometer, what is expected force between them? Without any calculation, we can guess that the force will reduce to 1/4 of this value. So by making this distance twice as much, the force will be reduced to 1/4 of its original value. If I make it 3 times as much, the force will be reduced by 1/9 of its original value. And if I make it 4 times as much, the force will be reduced by 1/16 of its original value. That means there is some rule at work here, and inverse square law is exactly means that. So when distance between the charges is increased, the force reduces as 1/r square. So this is the inverse square law. Whatever the distance, if you increase it, let's say you make it twice as much, you change r to 2r, and then you multiply it by the previous force that you calculated with r. So new force will be calculated that way, and this is the inverse square law. This simply means that force is following a rule which can be expressed graphically as well. And let's have a look at that as well. If this is the force between the charges and this is the separation, let's say when they are at a distance r, this is the force that they exert each other. So at any value, when one force exerts on the other has a certain value of f. But if you make it, let's say this is the distance r, I'm not taking it 0 here because at 0 it will be infinitely large, but let's say it's like this. That simply means that when you bring it close enough to make the distance 0, it will be infinitely large force that they exert in each other. So this is not going to touch this axis. But as you increase the distance, this force drops, and it drops as 1/r square, which means if at r it is a force F between them, at 2r it will reduce to 1/4 of this value. That means it will come here. So there is a steep fall in it. So this is a more realistic graph. At 3r it will be 1/9 of its value. So suddenly it will come here. So this is how this graph drops. So this is inverse square law of force. This force may be attractive. This force may be repulsive. It will be attractive in the case of opposite charges. This is something you already know from your O-level classes. And this is repulsive when they are like charges, whether they are positive or negative. So this is basically the introduction of electric fields. electrostatic, Coulomb's law of electrostatics. There are many other concepts that will follow, but I'm not going to stretch much because you already have a topic to cover, worksheets that I have shared with you based on the previous topic that I've given you. You complete that worksheet and I'll give you my feedback on it before the next class, inshallah. This is all for today. Inshallah, see you on Monday in the next week.